Hello again. We are back to discuss Unit 4 for statistics. Unit 4 starts in on probability, and this is where a lot of students do start to struggle with this a little bit. So please be patient with yourself and take the extra time to get to know this material well. Units 1 through 3 are things that many of us have seen before. We've seen graphs, we've seen mean, median, mode, maybe standard deviation might be new to us, but much of that material in the first 3 units is stuff that we have seen before, have some familiarity with. Probability for many is a whole new language and a whole new type of calculation. Our purposes of doing probability and statistics, now probability is a whole course on its own. You could take a whole probability course if you wanted to from a university. In statistics, probability is here for the purpose of analyzing data and deciding whether something is an unusual event or not. And as we go through this, we'll define what does an unusual or a highly unlikely event mean. So we'll start out with some of the basics of probability. So our key concepts here, single most important reason, like we said, is to interpret probability values and to see if we have highly unlikely events or events that rarely occurs. Such as, let's say something that has a probability of a 0.001, which means it's a 1 in 1,000 chance to occur. That's very rare. Well, that then becomes significant to us. The book talks a little bit about odds. We're going to skip over odds. This course, we do not talk about odds. That's more of a gambling application. So in the basics of probability, this book starts right in talking about events. Most textbooks define something called a chance experiment or a random experiment. And this book refers to that as just a procedure rather than a chance experiment. So if you hear me use the term chance experiment, I'm talking about that procedure. And it is simply an action with more than one possible result. And we cannot predict which result will occur. So an event is event is any of the possible results or outcomes from that procedure, that chance experiment. A simple event is a single outcome that cannot be broken down into any simpler components. For example here, if I'm rolling a die, a simple event might be rolling a 2. There is no way to break that down. But if I give you the event rolling an odd number, well, that can be broken down into rolling a 1, a 3, or a 5. So it can be broken down into other simple events. The sample space then is simply the collection of all the possible events from that procedure or that random chance experiment. So for this rolling a die, the sample space, you get a 1, a 2, a 3, 4, 5, or 6. That is the whole sample space. And we typically do use those squiggly brackets to contain the sample space. So some examples here. First, our first procedure we're going to talk about is a single birth. An example of a simple event would be having a girl. That would be a simple event. It can't be broken down any simpler than that. Or having a boy could also be a simple event. The sample space listed out, we can either have a boy or we have a girl. The second example is 3 births. Well, in 3 births, there are a lot of possibilities. They could all 3 be boys. We'd have 2 boys followed by a girl, or the girl could be the second of the 3, or the girl could be the first of the 3. Or we could have 1 boy first followed by the 2 girls, or the girl could be the boy can be in the middle, the boy could be the third one born, or all 3 of the births could be girls. So an event like saying 2 boys and 1 girl out of the 3 births, that is not a simple event because it can be broken down further. Because we could have the girl could be the third one born, the second one born, or the first one born. So there's 3 simple events that can be broken down into. So here, the example of the simple event, like I said, is one birth. Having a girl is a simple event, or a boy. It can't be broken down any further than that. If we have 3 births, however, if I name the exact occurrence, 2 girls followed by a boy, that's a girl, and a boy, that is a simple event because that defines a single one of those possible occurrences. For example, rolling a die, if the outcome is 5, that's a simple event. If I say it's going to be an even number, that's not a simple event because an even number could be broken down into a 2, a 4, or a 6. So back to the births again. Rather than saying, here I said 2 girls followed by a boy, that was girl, boy. Here I'm going to say just with 3 births, I want 2 girls and 1 boy, not specifying the order. Well, that could be 2 girls, then a boy, or it could be a girl, a boy, and then another girl, or it could be the boy first followed by 2 girls. So that is not a simple event because it can be broken down into other simpler, smaller events that do reach that standard. So that's our example. That's basically just a summary of procedures, events, simple events or non-simple events, and sample space. So moving on then, there's 3 common approaches to finding probabilities of an event. Some vocabulary, we're going to need P, just denotes that we're looking for the probability. Our events are usually labeled with capital letters. A, B, and C are the most common, but they could be any letter used. And so P with A in parentheses, that's read P of A, or the probability of event A. And that's asking for what is the probability that event A will occur. And when we deal with probabilities, so probabilities range from 0 to 1, with 0 meaning it is impossible. So probabilities that are close to 0 are very unlikely. It's not a very good chance they're going to happen. 0.5 means it's 50-50 chance, like flipping a coin. 0.5 probability of getting heads, 0.5 probability of getting tails. Could go either way. If it's a probability of 1, then we know it's certain. It's guaranteed to happen. In other words, there's no other possibilities. Again, probabilities of 1 and probabilities of 0 are not very common. But as a probability gets closer to 1, that means it's very likely to happen. Oops, that's not what I wanted. So there are 3 common. So back to those 3 common approaches. For our probabilities, of course, all have to fall between 0 and 1. And the notation we use is 0 is less than or equal to the probability of A, which is less than or equal to 1. Our first approach that we can use is called a relative frequency approximation. And the word approximation is in there because it is often just approximate. What happens here, we'll talk about simulations later, but it's often done with a simulation, is we repeat an event several times. Now, I mean a lot of times. And we look to see in how many of those procedures did we get the result that we're looking for. So it's the number of times that event A occurred divided by the number of times we repeated the procedure. An example here might be flipping a coin. If we flip a coin 1,000 times and we get 482 heads, our probability of getting heads, the relative frequency probability would be 482 out of 1,000. Classical probability, sometimes referred to as theoretical probability in some textbooks. Classical probability is the most common one. Its weakness is, though, it requires something called equally likely events. That means that every possible outcome, every possible event has exactly the same chance of occurring. Rolling a die would be an example of this because we assume pretty much at least that each side of the die has the same chance of occurring, that it's equally balanced. If it's a fair die, that would work. If we throw marbles in a box, if we put 50 marbles in the box and there are 10 red ones and 40 blue ones, as long as the marbles are the same size, same texture, if we reach into the box without looking, there's an equal chance of getting any of those 50 marbles. That's equally likely events. And so the probability, the classical probability then, is the number of ways that A could occur divided by the total number of possible simple events that could occur. And then finally, we have subjective probabilities. And subjective probabilities are often misunderstood. Many people say, well, it's just an educated guess. It's a little bit more than that. It's an estimate, but it's based typically on history. So this occurs often in sporting events. Let's say Team A has defeated Team B 17 of the last 20 games. Well, that is the history, and we would start there. But then, of course, we bring in other factors, relevant circumstances. Maybe Team A's quarterback is hurt. That might change our probabilities. Maybe the weather is snowy and Team B does not play good in cold weather, does not play well in cold weather. That could change our probability. So we're starting with that history and we're adjusting for those other relevant circumstances. And that's where the subjective part comes in, is different people might adjust it more or less for those circumstances than others. So yes, two people are going to look at a situation and come up with different subjective probabilities, but they should be relatively close because they're all starting from that same history. So simulations are a tool used often for calculating the relative frequency probabilities, where rather than actually doing a procedure, we simulate the procedure. And we do it over and over again, testing to see what the frequency is of each of the possible events, and we can use that then to estimate or to calculate probabilities. When we are calculating probabilities, it is always best, if you can, to give an exact fraction. So by an exact fraction, I mean like 2/3, 2 out of 3, 5 out of 9, because it is that 2 out of 3 is saying we have 3 possible outcomes, and 2 of them would give us what we want. If we can't express it as a simple fraction, then we're saying to round it to 3 significant digits. Significant digits mean non-zero digits. So once the zeros stop, once a non-zero number starts, we go 3 digits past there. So it could be, obviously it's less than 1, so it could be 0.375. That would be 3 significant digits. But if these first digits are zeros, we would have to keep going. So that would also be 3 significant digits. These zeros at the beginning do not count. The law of large numbers. So this is where probability really has it's the mainstay of probability, but it's also where probability comes in and connects with statistics. What the law of large numbers is saying is the more often we repeat something, the more trials we complete, the closer that probability gets to the real true probability. For example, let's look at flipping a coin. And let's say we're going to repeat it. I'm going to call it trials, is how many repetitions. Let's say we do it 10 times and we get 3 heads. Well, that's a 3 out of 10 probability of getting heads. That's only a handful of trials, only 10 trials. But if we did 1,000 trials and get 482 heads, well, that 482 out of 1,000, because we repeated it more times, we had a large number of repetitions, that should be much closer to the true probability of getting heads than this first one where we only had 10 trials. So it applies to behavior over a large number of trials. We have to be careful. It does not apply to a single individual outcome. An individual outcome could could be one of those unusual events. If we know nothing about the likelihood of different possible outcomes, then we can't assume, first of all, that they're equally likely, and we have to be careful about that. And the actual probability might depend on other factors that could be difficult to test. So, talking about that, assuming things are equally likely, we mentioned rolling a die. We assume that each side of the die coming up is equally likely. But there have been studies done showing that the manufacturing process can change that. The little divots that are put in there for the numbers can unbalance the die. So that assumption might not be correct. So examples where we would want to use each type of probability. If we want to know what is the probability the commercial airliner will crash, we cannot use classical or theoretical probability here because they're not equally likely. The chance, crashing or not crashing are definitely not equally likely. If they were, we'd never get on an airplane again. So it makes more sense to use a relative frequency approach here. So we study, we find that last year there was 39 million commercial flights. Of those, there were only 16 crashes. So our relative frequency probability is the number of crashes over the total number of flights. So 16 over 39 million gives us 0.000000410 probability. That's a pretty small probability. Relative frequency or class had to be used here because the classical approach could not work again because it's not equally likely. Crashing and not crashing are definitely not equally likely here. If we didn't have all that historical evidence of 16 crashes out of 39 million flights last year, we could use subjective probability to estimate. But when we have large numbers like 39 million flights, a lot of times, even the estimation, we can't imagine those large numbers like that. So another example here, a little bit of a corny example, but the Pew Research Center interviewed people and found that 366 of those that responded said yes, they feel they've been in the presence of a ghost. And 1,637 said no, they don't feel like they've ever been in the presence of a ghost or have not ever seen a ghost. So we want to find the probability that a randomly selected person from this group would respond yes. First thing we need to find is the total. We add up the 366 yeses and the 1,637 no's to get a total of 2,003 people that responded to the survey. So then to find the probability that they would respond yes, there's 366 yeses out of 203 total responses. Again, that's not a simple fraction, so we would divide that out into a decimal to make it easier to interpret. To get 0.183 is that probability. So there's a 0.183 probability that a randomly selected adult says they have seen a ghost. So this is an example, this interpretation, of extending now this sample out to the entire population. 2,000 is a pretty big sample. 2003 was the size of the sample. That's big enough that we could say it's probably representative of the larger population. So we had 0.183 probability of a randomly selected person in the sample saying they've been in the presence of the ghost. We extend that to the whole population saying, yeah, we feel there's about a 0.183 probability that any randomly selected adult would say they've been in the presence of a ghost. The complement rule. So the complement is the opposite. It's the probability that the event we're looking at does not occur. And it's usually denoted with that little slash over the top, that line over the top. A bar, sometimes called, or the complement of A. It's also the not symbol. So sometimes it might be pronounced as not A. So the probability of A is the probability that A will occur. Probability of A bar is the probability that A will not occur, or the probability that the complement of A will occur. So if we let A be rolling the die again, let's say it's rolling 2, A bar would be a 1, a 3, a 4, a 5, or a 6. Everything but what's in A. Now, of course, A is actually the complement of A bar as well. For two things to be complements, they must add up to the entire sample space, or the probability must add up to 1. It can be very useful. Let's say, looking back to the Pew Research, we have a sample of 2002 adults randomly selected. 1,782 of them respond that they use the internet. We want to find the probability that a randomly selected adult does not use the internet. So there's two ways we can handle this. We could subtract in our raw numbers, our raw frequencies. Of the 2002, 1,782 said they used the internet, so we subtract 2002 minus 1,782 gives us 220 that do not use the internet. So that's 220 out of 2002, giving me 0.110 probability that a randomly selected adult does not use the internet. We could have done that doing the probability first. The probability that a randomly selected adult does use the internet would be the 1,782 over 2002. That's going to give me a probability of 0.890. So then the probability of the complement, which is the probability of not using the internet, I'm just going to put probability of not, ... because I don't have room to write it out, is just going to be 1 minus the 0.890, which is the 0.110 that we calculated before. So identifying significant results and probabilities. This involves rare events. So if we make an assumption, and this is a mainstay in statistics, we make assumptions. So we make a given assumption. If the probability of a certain event occurring is either really small, but then it does occur, well, then we assume that assumption had to be wrong. The other is true as well. If the probability of a given event occurring under that assumption is really, really likely, but then it doesn't occur, well, again, we might assume that assumption was wrong. So identifying significant results, typically we use a probability of less than 0.05. It's kind of the standard. But sometimes if we have more critical things, we'll go to a smaller probability, or less critical things, we might go to a larger probability. So that 0.05 is not set in stone. It can be adjusted based on the situation. So these rare results, or these highly unlikely results, can occur in one of two ways. If we have more successes than what we would expect under the assumption, then we would assume the assumption was wrong. If we're assuming the dice is fair and we roll it 1,000 times, so we're rolling a single die, and let's say we get 450 times that we roll a 2 out of 1,000 rolls. Well, we'd only expect 1/6 of them, or 166 or 167 of them to be 2s. 450 is significantly larger than what we expected. That we'd have to calculate the probability, but that might make this an unlikely event. The opposite could also be true. If we have significantly fewer, so we expect 167 2s out of our 1,000 rolls, but then we only roll 2 24 times. Well, that's significantly lower than the 167 we expected. So that might be, we calculate that probability, that might be a highly unlikely event. Either way, rolling 24 2s out of 1,000 or rolling 400 2s out of 1,000, both of them are reasons to start questioning whether the die is a fair die or not. So a quick review of probabilities. All probabilities have to be between 0 and 1, with a probability of 0 meaning that something is impossible, and a probability of 1 meaning it's guaranteed to occur, it's certain to occur. The notation P of A is saying that's the probability that event A will occur. And P A bar is the probability that A does not occur, or the probability that A's complement will occur. So the rest of section 1 talks about odds. We're not going to go into odds in this course. So we're going to go on into section 2. So starting out in section 2, then we're moving into looking at simple events versus compound events and combining probabilities for multiple events. And in section 4.2 here, we're looking specifically at the addition and multiplication rules. So addition rule is used when we're looking at a situation we want to find the probability of A or B. So probability A or B means that A could occur, or B could occur, or both could occur to satisfy that probability, that desired outcome. The key thing there is addition rule deals with or. The multiplication rule, on the other hand, we're looking at the probability of A and B. So the addition rule, we're looking at a single procedure, a single action, getting and combining the possibility of multiple results. For the multiplication rule, we're looking at 2 or more actions. We're repeating the procedure more than once. And we're looking at events occurring from one procedure to the next. And so A and B is saying that we get A to occur in one of the procedures and B in the other procedure. And we're going to, what is that combined probability? So here the key is the word and tells us we're using the multiplication rule. So some vocabulary: compound events, or when we have an event that is made up of combining 2 or more simple events. Typically, we're repeating a procedure, or we're doing more than one or doing multiple procedures. So in the addition rule, we're looking at a single trial of a single procedure. So we're only doing the procedure once. Either the event A could occur, the event B could occur, or both could occur. So an example of this is, let's say event A, again, rolling a die, is getting a 2 or a 3. Event B is getting an even number, so a 2, a 4, or a 6. Well, 2 is in both of them. So it's possible that if we roll a 2, we've satisfied both event A and B. But the probability of A or B here, we have 2, 3, 4, 5, or 6. That's 5 of the 6 outcomes of rolling the die. The only thing that wouldn't satisfy one of those 2 events would be rolling a 1. We could go through the addition rule process as we go through these. Probability of rolling an A is 2 out of 6. Probability of satisfying event B on that roll is 3 out of 6. Probability of both is 1 out of 6. That would be the 2. So if we look at our addition rule coming up, we would add these probabilities. 2 6 plus 3 6 would be 5 6ths. And then subtract the probability of both, because we don't want to repeat that. Both of these probabilities included getting a 2. So we subtract out the 1 6 to get 4 6, or a 2/3 probability. So the intuitive addition rule, we just saw kind of a formula there, but it's basically saying you need to count all the different ways that either of them can occur without repeating any of those counts. So that's why we had to take out the 2 up here. We subtracted this probability because the 2 was in both of those original events. We don't want to repeat the 2 in our probability calculation. So the formal addition rule, probability of A or B is found by adding the probability of A plus the probability of B. That's what we did here. Probability of event A plus the probability of event B gave us the 5 6ths. And then subtracting out the probability that both would occur. And that's why we had to subtract out that 1 6th. That's the probability that both would occur, because 2 is in both of those events. So disjoint events, most textbooks refer to disjoint events as mutually exclusive, which means both of them cannot occur at the same time. Or if we know one has occurred, the other one cannot occur. An example might be rolling the die. If we roll a 3, well, then we know we can't roll a 5. Those are mutually exclusive or disjoint events. So here, an example of disjoint events. If we're selecting someone for a clinical trial, either they're male or female. They cannot be both. If we know the person we selected is male, they cannot be female. So those events A and B there are mutually exclusive or disjoint events. Events that are not disjoint, well, I could randomly select someone who's taking a statistics course or select a female. Well, it's possibly both. You can be female and taking a statistics course. So those are not disjoint events. They're not mutually exclusive. So our summary here, to find the probability of A or B, first we need to make sure we associate the word or with the addition rule. And it's found by adding up the ways that each of them can occur and subtracting the ways that they both occur. So we're avoiding the double counting. Complementary events, before we go any further, probability of complementary events comes into the addition rule. We said complementary events, A or not A. So A can either be read as the complement of A. A bar can either be read as the complement of A, or it can be read as not A. It means the same thing. Those two complements have to encompass the whole sample space. So the probability of A plus the probability of its complement has to add up to 1. So because of that, the probability of A or A bar is 1. The reason for that, of course, is the probability of A and A bar is always 0. They're mutually exclusive. We can't be in A and not in A at the same time. So that's why we do not have to subtract off that probability of being in both in that case. But this relationship gives us several formulas that we can use for calculating probabilities. Like here, probability of A plus the probability of its complement adds up to 1. We can use our basic algebra to rearrange it, though. The probability of the complement is 1 minus the probability of A. Or the probability of A is equal to 1 minus the probability of the complement. This occurs quite a bit as we get into some more advanced probability calculations, where we find that the complement is much easier to calculate than the probability that we're looking for. So we find the probability of the complement and then just do this. We subtract it from 1 to get the probability of the event we're trying to find. Sometimes it's just the information we're given. Like in this example here, based on a survey, the probability of a randomly selected household in the U.S. having a smartphone is about 0.87. Now, this PowerPoint was made a few years ago, so it might be higher than that now. So the probability of having a smartphone is 0.87. What if we want to find the probability of not having a smartphone? Well, the probability of not A equals 1 minus the probability of A. So that's 1 minus 0.87, which is going to give us 0.13. So we see that calculation played out here. Next, we move on to the multiplication rule. So as we said, the addition rule was all just one occurrence of a single procedure. The multiplication rule, we're looking at multiple trials of that procedure. We're repeating the procedure at least a second time, maybe more. So the probability of A and B is the probability of getting A on the first trial and B on the second trial. Some notation now, probability A or probability B, that vertical slash there is a conditional indicator. It's pronounced given. So it's saying the probability that A occurs given, or probability that B occurs given that we know A already occurred. So it was the probability of B occurring assuming that A has already happened. So the intuitive multiplication rule is if we have two things to occur in back-to-back trials, we'd multiply their probabilities together, but making sure the second one is found assuming the first one had to occur. If the first trial is unsuccessful, there's no reason to even go on to the second trial. So if we look at the formal wording here, probability of A and B occurring in consecutive procedures is the probability that A occurs. And then for the probability that B occurs, given that A has already occurred. Now, what that means depends on the circumstances of the study. Let's look at marbles in a box. So let's say we have 40 red and 10 blue marbles in a box. If I want to look at the probability of drawing a red and then another red. Now, there's a term that's going to come up later called without replacement. What we're going to do is we're going to draw out the first red marble, and we're not going to put it back. So the probability that the first one being red, oops, got to erase that. Is 40 out of 50. Probability that the second one is red, given that the first was red, well, there's now only 39 red marbles out of 49 marbles in the box. So we'd have to multiply that out. On top, we have 40 times 39, giving us 1,560. On bottom, we got 50 times 49, giving us 2,450. We divide that out to get 0.637 is that probability. So that's what this notation meant here of given that the red already occurred, that means there's only 39 red marbles left out of 49 total. Independence. So two events are independent if knowing that one has occurred does not affect the probability of the other. So up here, these were not independent. Getting red on the first marble is not independent of getting red on the second marble. Because once we knew the first one was red, that changed the probabilities here. If the first one was blue, this would be a very different probability as well. But there are ways that we can alter that. So let's look at an example here. I'm looking at drug testing. So I have 50 subjects who were tested, 45 tested positive, and 5 negative. So that's the total of 50 subjects. If 2 of these subjects are randomly selected, and the term here is with replacement. So that means we randomly select one subject, we test them, and then we put them back into the group. So when we randomly select the second subject, it's possible that we can select the first one again. This is with replacement, and we're going to see how this comes out to be independent events. The second example is we're going to repeat this, but this time without replacement. So we randomly select the first person, we test them, and then we send them on their way. So we don't put them back into the group. So now there's only 49 subjects left for the second person. When we randomly select that person, the probability that they will test positive depends on whether the first person tested positive. So here, with replacement, we put the person back. If we randomly select the first person, there's 45 positives out of 50. We put that person back before we draw the second one. Well, there's still 45 positives out of 50. So the chance of the second one being negative is still 5 out of 50. If we had not put that person back in there, that chance would have changed to 5 out of 49, as we'll see here. So if we multiplied this, the chances of the first one being positive and the second one negative is 45 out of 50 times 5 out of 50, giving us 0.0900. But if we change that to being without replacement, so we test the first one, and we send them on their way, so there's only 49 to draw from for the second one. The probability that second one's going to be negative, there's still 5 negative people if we assume the first one was positive, but there's only 49 people left in the group. So that's now going to be, instead of 45 over 50 times 5 over 50, it's 45 over 50 times 5 over 49. Changing it from 0.0900 to 0.0900 to 0.0918. so it slightly changes the probability. So in this case, these were not independent. These were dependent events because the probability of the second person being negative depended on whether the first person was positive or negative. But when we were doing with replacement up here, the first person being negative, that probability doesn't matter whether, the second person being negative, doesn't matter whether the first person was positive or negative because we put them back into the group. So sampling. With replacement means the selections end up being independent because the chances are the same from one selection to the next. The population, the whole group we're selecting from, is the same from each selection to the next. If we don't replace them, then they become dependent events, and that's where that conditional probability comes in. Now, because this type of situation comes up a lot, they use something called the 5% rule or 5% guideline. If the number of items we are choosing is less than 5% of the size of the population, we can assume they're independent just so that we don't have to go through some really complex calculations. So for example here, if we're calculating here drug screening and we're testing, there's 130,639,273 full-time employees in the United States. And history tells us the probability of a randomly selected employee testing positive for drugs is 0.042. And I want to randomly select 3 of them. So where are we at here? And we're going to select 3 employees to see what's the probability that all of them test positive. Well, adjusting this probability for taking 1 out of 130 million just isn't practical. That probability is not going to change much at all by removing 1 from that probability. So this is where that 5% guideline comes in. 3 is definitely less than 5% of 130 million. So we don't need to worry about adjusting that probability. We're just going to take 0.042 chance of the first one being positive times the 0.042 chance of the second one being positive times a 0.042 chance of the third one being positive to get an overall probability that all 3 will be positive of 0.0000741. So an application of the multiplication rule comes in redundancy. So redundancy it's an engineering thing. It's something I worked with a lot when I did engineering work. We have a lot of redundancies when we calculate stuff. The human body has redundancies. Genetically, we might damage one DNA strand. There's that same quality or that same function is encoded in a different spot in our DNA. The example that I often use in class is a commercial airliner. If you've ever been on a commercial flight, almost guarantee that there was a mechanical failure on that flight. Pretty much every commercial flight has a mechanical failure. But it doesn't crash because there's a redundant system. One system stops working, there's another system that kicks in and performs that function for it so that the flight can successfully complete its trip. So here's an example of the Seagate hard drive. I'm not going to say the model number, but its probability of functioning, or the probability that it'll failure over 1 year of use is 2.89%. So 0.0289 probability if we're converting that into a probability. So there it is, the 0.0289 probability. If we have a single hard drive, the probability that it'll go 1 year without failing, that's the complement of failure. So it's just going to be 1 minus the probability of failure. 1 minus 0.0289 gives us 0.971, or 97.1% that probability that hard drive will function correctly throughout the full year. But if we add in a redundancy, so we have 2 hard drives. So everything that's on one hard drive is backed up on the second hard drive. The probability of getting through the full year, well, we have to start out with the probability of failing. This is where we said sometimes the probability of the The complement is easier to calculate. So we're going to look at the probability that both hard drives fail, which is the 0.0289 times 0.0289. So at 0.0289 times 0.0289 gives us so that's scientific notation. That is saying 8.35 times 10 to the negative fourth, which is 0.000835, which we're just going to round off to 0.001. That's the probability that both of them fail. So 1 minus 0.001 gives us a 0.999, or 99.9% chance that between the two hard drives, we get through the year without any issues with our data. So that's our summary of that example. With only one hard drive, the failure rate is 2.9%, or 0.0289 probability. But if we have two hard drives, it's only a 1 in 1,000, or 0.001 probability that there will be a failure throughout the year. So that's where redundancy is a huge issue in engineering. Even with a very low probability of failure, you can see how using a redundancy drastically shrinks that probability of failure. So our summary for this section, the addition rule applies when we're looking at the probability. Again, it's a single occurrence. We're looking at only one procedure being done here. A or B, remember, is associated, the OR is associated with the addition, and it's found by adding those probabilities without repetition, making sure we count each one only once. So that formula, probability of A or B, was the probability of A plus the probability of B, that's where the addition comes in, minus the probability that they both occur at the same time, A and B. The multiplication rule applies for two occurrences so we're repeating the procedure at least twice, so two trials are being completed here. The word and should be associated with multiplication. And P and B is found by multiplying those, again, making sure we account for the fact that the first event has occurred. So the probability of A and B is found by taking the probability that A occurs in the first trial times the probability that B occurs in the second trial, given that we know A occurred in the first. That is the end of section 2. We'll be back later for section 3.